So now we know that a matter wave is described by a wave function, which I've been carelessly just calling psi. Now I'm going to write it as a capital psi, and it's a function of all three position coordinates and time. Now for our purposes, it's going to be useful to separate out the time dependence. We have a simple oscillating time dependence, e to the minus I omega t, where what happens is that the energy, which we know is equal to Planck's constant times the frequency, well, that's Planck's constant over 2 pi times 2 pi times the frequency. 2 pi times the frequency is just omega, and this is h bar. So the energy is h bar omega. By setting this oscillating time dependence, we're essentially saying we're looking at states with a definite energy. And we factor out this part with a lowercase psi, which is basically a standing wave solution to a wave equation. Notice it has only position dependence because we factored out any dependence on time. Now the question is, what formula, what wave equation do we use to figure out this wave solution here? It turns out that's an equation known as the Schrödinger equation, after an Austrian physicist named Schrödinger. This is not the form we normally put it in, but it's useful for our basic understanding here. It says the second derivative of the wave function plus a bunch of constants, including the mass of the electron, times the energy minus any potential energy function we might have, all multiplied times the wave function, equals 0. So what I'd like to do is we're going to use this to find the solutions for a constant energy without a potential. And what we'll find is that they are simple plane wave solutions.